Organic Chemistry, Part 3, we will be looking at organic compounds and their physical properties. There are four different types of isomers: structural, chain, positional, and functional. Structural is an organic molecule with the same molecular formula but different structural formula. You can see in this case, there is the same molecular formula. If you count the number of C's and H's, they are the same, but they are in different structures. Here there's a branch, and here there's no branch. Chain. Same molecular formula, but different types of chain. Here is an example. This is a straight chain. There's one branch here, and there's three branches or two branches in this case. Positional, same molecular formula, but different positions of side chain, substitutions, or functional groups of the parent chain. As you can see here, the Cl and the H are swapped around, but they do have the same function because the double bond O stays at the exact same place. Functional, same molecular formula, but different functional group. They have the exact number of carbons and the exact number of H's, but the double bond O changes the function. This double bond O is on the first carbon, which makes it an aldehyde, and this is on the second, which makes it a ketone. We will now look at each compound and their physical properties. We first get van der Waals forces, and then hydrogen bonds. Van der Waals forces consist of London forces and dipole-dipole forces. London forces are very weak and non-polar molecules. These are the alkanes, alkenes, and alkynes. Dipole, they are polar, and they are slightly stronger than the London forces. These consist of aldehydes, ketones, esters, and haloalkanes. Hydrogen bonds are also polar. These are the strongest molecules. These are alcohols and carboxylic acids. Take note of this. The number of carbons affect the melting point and boiling point. If there are more carbons, melting point and boiling point increases, and if there are less carbons, melting point and boiling point decreases. Comparison between alcohol and carboxylic acids. This is a very famous question they like to ask in exams and tests, and they usually ask which one is stronger, alcohol or carboxylic acid. Use this as a standard answer. Both are very polar and have strongest intermolecular forces. However, carboxylic acids has stronger H bonds than alcohols because there are two H bonds in the carboxylic acid. Alcohols are only able to form one hydrogen bond between adjacent molecules. Thus, the carboxylic acid is stronger than an alcohol. Substances with weak intermolecular forces will vaporize easily, thus have a higher vapor pressure. Substances with high intermolecular forces will vaporize slowly, thus have a lower vapor pressure. In this case, there's a liquid. The liquid molecules are packed tightly together, thus have a stronger intermolecular forces. There's little evaporation, thus lower vapor pressure. In here, there's a gas. The gas molecules are farther apart, so there's weak intermolecular forces. It evaporates easily and have a higher vapor pressure. Smell. Weakest intermolecular forces will be smell first and vice versa. The weakest intermolecular forces will be smell first because the bonds are overcome easily, thus letting out the smell. Shorter chain hydrocarbons are more flammable as they have the lowest molecular weight. Alkenes are more reactive than alkanes because of the double bond, thus more flammable. Chain length. Chain length means the number of carbons. Molecules with strong intermolecular forces will have a higher melting point and boiling point, as there is more kinetic energy required to break the intermolecular forces to change phase. Chain length of molecules increase, melting point and boiling point of hydrocarbons gradually increases too. The reason for this is the smaller the molecules, the smaller the surface area over which the intermolecular forces act in comparison to a longer chain, which has more intermolecular forces, thus more energy required to remove the forces. In this case, this is a straight chain hydrocarbon, and this is also a straight chain hydrocarbon. However, this has more carbons and this has less. Thus, this will have a higher melting point and boiling point, and this a lower melting point and boiling point, because the chain length here is greater than of this. Branch chains. More branched hydrocarbons means lower the boiling point because it is more compacted, thus a smaller surface area, weak van der Waals forces, and less contact points. Less branched hydrocarbons means a higher boiling point because it is less compacted, thus a larger surface area and more points of contact. So, if it's more branched, it's more squashed together, thus a smaller surface area. And in this case, this one is more branched, and this is less branched. Thus, this will have a lower boiling point, and thus a greater boiling point. Now, look at past paper examples to see if you understand this concept. The first one, learners investigate factors that influence the boiling points of organic compounds. The boiling points of some organic compounds obtained as shown in the table below. The first step to do when you're given a table like this is to identify what these compounds are. A, B, and C, and D are all alkanes. However, D has a branch. E is an alcohol and F is an aldehyde. The first question is, the boiling points of compounds B, C, and D are compared. Is this a fair comparison? Choose from yes or no. Give a reason for the answer. B, C, and D are all alkanes. However, B has 4 carbons, C has 5, and D has 5 carbons. So, this is not a fair comparison. There is more than one independent variable, the molar mass and the chain length. Chain length being number of carbons differ and the molar mass differs. The second question, how do boiling points vary from compound A to compound C? Choose from increase, decrease, or remain the same. Explain the answer. A is negative 42 and C is 36. Thus, it increases. It increases in molecular mass. The strength of the intermolecular force increases, and more energy is needed to overcome or break the intermolecular forces. The next question is, which compound, D or E, has a higher vapor pressure? Give a reason for your answer. D is an alkane and E is an alcohol. D has the higher vapor pressure because it has the lowest boiling point. Here is another past paper example. An investigation was conducted to determine the effect of one of the factors on the boiling points of the alcohols. 3 straight-chain primary alcohols, P, Q, and R, were used. The results obtained are shown in the table below. Since they have given us that this is an alcohol, we don't need to identify the compounds. The first question is, which one of the alcohols have the highest vapor pressure? Choose from P, Q, or R. Give a reason for your answer. You first look at the boiling points. This is the highest, this is the lowest, and this is in between. For something to have a highest vapor pressure, it needs to have the lowest boiling point. Here is the lowest boiling point, so the answer is P. P because it has the lowest boiling point, or P because it has the weakest intermolecular forces. The next question is how could the boiling points of a straight-chain compound, which is C6H14, compare to that of an alcohol Q? There's alcohol Q with the highest boiling point. Fully explain the answer and choose from greater than, less than, or equal to. Here is the C6H14 if you needed to see it, and the answer is less than. The intermolecular forces between the molecules of alcohols are hydrogen bonding, because this is an alcohol, whereas this is an alkane. Intermolecular forces between molecules of C6H14 are only London forces. If you go back to the previous slide, you will see that London forces have an alkane, and this is an alkane. London forces are weaker than hydrogen bonding. Less energy is needed to overcome the intermolecular forces in C6H14, and more energy is needed to overcome the intermolecular forces in Q, because Q is an alcohol, whereas C6H14 is an alkane. This is the last past paper example we'll be doing, so I want you to try it first before you look at the answers. The boiling points of 5 organic compounds represented by the letters A to E are given in the table. Here are the compounds. Ethane, alkane, butane, alkane, methylpropane is an alkane with a branch, pentan-1-ol is an alcohol, butanoic acid is a carboxylic acid. The first question, explain why compound B has a higher boiling point than compound C. Compound B is here, and compound C is here. The boiling point is higher in compound B because it's a straight train with no branches, and C has branches. So, the structure, compound B has a larger surface area than compound C because it has a straight chain. Intermolecular forces, the intermolecular forces in B is shorter than in C, and more energy is required to overcome intermolecular forces in B than in C. The next question, compound D and E have the same molecular mass but different vapor pressure. Which compound, D or E, has a higher vapor pressure? Fully explain the answer. D and E. This is an alcohol, this is a carboxylic acid. This should ring a bell in your head because we did this previously. D. Because D is an alcohol and this is a carboxylic acid. This has a higher vapor pressure because it has a lower boiling point. It has a lower boiling point because it can only form one H bond and this can form two H bonds. Both compounds have hydrogen bonds. Compound D has one side for hydrogen bonding and compound has two sides for hydrogen bonding.